Alright, let's work some problems. First of all, diffraction gratings. I shine a laser with a diameter of 1 millimeter onto a diffraction grating. The grating has lines separated by 3.4 microns. On a wall 1 meter away, I measure that the m equals 1 diffraction peak is 12 centimeters from the m equals 0 peak. What is the wavelength of the laser? Okay, so what's happening here? I've got a laser beam, I'm shooting it, I hit a diffraction grating, and that causes spots on my wall over here, alright? The m equals 0 spot is right where my laser beam was headed anyway. But then I get my m equals 1, it's up here, some angle away. Now I know this distance, right? We're told that they're 12 centimeters apart on a screen which is 1 meter away, and so I can get the angle of these between these two peaks because tangent of that angle is just going to be the height divided by the length, right? But what does that angle have to do with the wavelength of the light? Well, just like in a two-slit interference pattern, when I have my diffraction grating, I get constructive interference when adjacent slits contribute light way off on my screen who've taken a path which differs by an integer number of wavelengths, right? And we said, boy, if that's my angle right there where I'm seeing this peak, and this distance right here is d, the spacing between slits, all right? That angle is the same as that angle right there, and then that distance right there, the extra path that this one travels relative to that one, is just going to be d sine of theta, and we want that to be an integer number of wavelengths, all right? So for m equals 0, we're right here on the axis. M equals 1 is the one up here, all right? And the angle for m equals 1 is, I can solve that in terms of the wavelength, or I can find the wavelength in terms of that angle, because I know that angle, all right? So the wavelength is just going to be d sine theta divided by m, right? And I know the angle for the m equals 1 peak, so the wavelength is just going to be d sine, and the angle for the m equals 1 peak is going to be the inverse tangent of h divided by L, and we divide that all by m, which is 1, all right? So the wavelength is just going to be d, which was 3.4 times 10 to the minus 6 meters, right, times the sine of the inverse tangent of h, which was 12 centimeters, so 12 times 10 to the minus 2 meters, divided by L, which was 1 meter. Our units cancel here. That's good because arctangents shouldn't take units. Alright, and then we can go and plug this into our Python calculator, and we're going to have 3.4 times 10 to the minus 6 times the sine of the arctangent of 12 times 10 to the minus 2 divided by 1. No thank you, Java. Doing something right now. Divided by 1, and we get 4.05 times 10 to the minus 7, or 405 nanometers. Yay! It's a purple laser pointer with one of those little diodes they use in Blu-ray players. Okay, so there it is. There's our answer. That's the wavelength of our light. Now, how well do you trust your wavelength measurement from the previous problem? Right? We don't make our measurements perfectly, but let's assume that we measure everything very, very well so that we're limited only by the resolving power of the grating. What's the resolving power of a grating? Well, we said when we're measuring wavelength, we define resolving power to be lambda divided by delta lambda, and we said in the video, or in the book, that the resolving power of a diffraction grating is just the number of lines illuminated multiplied by the order that we're using. The order we're using is 1. We just need to know how many lines are illuminated. But as you recall, if you go back and look at the original problem, I gave you a piece of data we haven't used yet, and that is that the diameter of the laser beam, let's call it, I've already used little d, let's call it big D, is 1 millimeter. Alright? So if I've got this laser right here and I've got these lines with a certain spacing, how many lines do I illuminate? Well, it's not fair maybe to count this line or this one as much as this one because less light is illuminated in and so forth. But this is sort of an order of magnitude, I mean sort of not order of magnitude, but rough sort of Rayleigh's criterion kind of measurement of the resolving power. So let's just calculate the number of lines illuminated as the diameter of my laser beam divided by the distance between the lines. How's that? So that means our resolving power is just going to be, which is lambda over delta lambda, that's just going to be d over the spacing between the lines times m, which is 1, right? And so the uncertainty, kind of the how well I can measure my wavelength, is just going to be the wavelength times spacing between lines divided by d times m. All right, and we said this is 405 nanometers. And d was 3.4 times 10 to the minus 6 meters. And the diameter of my laser beam was 1 times 10 to the minus 3 meters, and then m was just 1. All right, so we plug that into my calculator, and we get 405. Let's just do this in nanometers. These units over here are going to cancel out. So 405 nanometers times 3.4 times 10 to the minus 6 divided by 1 times 10 to the minus 3. There we go, 1.3738. 1.38 nanometers. So I really haven't measured the wavelength very well. If I wanted to do better, I need a better resolving power, which means I could use a higher diffraction order, or I could expand my laser beam before I hit the grating so I illuminate more of them, or I could use a grating with a smaller spacing, d. Alright? Single-slit diffraction. You shine a green laser pointer with a wavelength of 532 nanometers at one of your hairs. On a wall 45 centimeters away, you see a diffraction pattern. The distance from the zeros on either side of the central bright fringe is 14 millimeters. What is the diameter of the hair? All right, so here we go. We've got a green laser pointer, all right? And we're shining it onto a hair. Well, what happens when we shine it onto a hair? Well, a hair is like the inverse of a slit, all right? So you can imagine what happens is we shine this laser beam, I put my hair here and block some of it. What I'm going to get is, imagine if I had a slit here this size instead, I'd get a diffraction pattern, right? Whatever, all right? Now what we're going to do is we're going to take the inverse of that. So now by putting the hair there, I'm going to get the laser beam minus the diffraction pattern. So my laser beam's this tiny little spot here minus my diffraction pattern. But if I take an electric field and multiply it by -1, it's the same intensity, right? So minus a diffraction pattern is really pretty much the same as a diffraction pattern. So what did I just tell you? I can work this problem as if instead of having a hair blocking my light, I really had a slit, which was the size of my hair, and I can work it the same. Okay, so now the diameter of my hair then is just the diameter of the width of the slit. How big is my slit? Well, you're told that you have a diffraction pattern, and the distance from the zeros on either side of the center, you get some number, and let's call that, let's call it Q for kicks, all right? So Q is the distance between those two. So I have my laser beam, I go through my slit, and I'm going to get these two zeros out here, right? And what are the angles for those zeros? Well, the angle to go up to the first dark area, the first zero, remember for a single slit, that's given by the equation A sine theta, where A is the width of my slit, right? That's what I'm trying to find. That's the diameter of my hair. When that's equal to an integer number of wavelengths, that's when I get a dark area. Remember, for a diffraction grating, or for a 2-slit pattern, or a 3-slit pattern, this equation, if I put the D here, replace A with the spacing between the slits, that tells me where I get bright spots. But with a single-slit pattern, I put the width of my slit, and this actually gives me the angles where I get darkness. All right, if you don't remember why, go back, look at the book, or rewatch the video. All right, but this is going to tell me where the darknesses occur. So I know how far apart these dark spots are on either side of my central peak. That is Q. All right, so if I look at this right here, this distance is Q over 2. This distance is how far my screen is. All right, so tangent of theta then is just going to be Q over 2 divided by L. All right, so I can find the diameter of my hair. That's just A right here. A is equal to m lambda over sine of theta, but sine of theta is just, tangent of theta is this. So it's going to be sine of the arctangent of Q over 2 L, all right? And that's going to be equal to, well, m is equal to 1, right? We're using the m equals 1 on either side of this. All right, lambda we said was 532 nanometers, and we're going to divide that by the sine of the arctangent of, what did we say q was? I forget. Q is 14 millimeters, and d is 45 centimeters. So 14 times 10 to the minus 3 divided by 45 times 10 to the minus 2. They're both in meters. That cancels out. We go to our calculator. We're going to find the diameter of our hair then. It's 532 nanometers divided by the sine of the arctangent of 14 times 10 to the minus 3 divided by 45 times 10 to the minus 2. And we get 17.05. All right. Oh, q divided by 2. Whoops. I made a mistake. Right? Because remember, this angle has to do with half of that distance out to the 0. Because we're looking at it as we're given the distance between the two zeros on either side. So let's go in and fix this. We need to divide this by 2. And then we get 3.42 times 10 to the minus 5, or 34.2 microns. That's the thickness of the hair that made this pattern. All right, there's an example for you. All right. Rayleigh's criterion. A microscope has an objective with a focal length of 3 centimeters. It is 5 millimeters in diameter. If the objection is diffraction limited, in other words, it's a very well-made lens, what is the size of the smallest thing you could possibly resolve using this objective? Use a wavelength of 450 nanometers, the shortest visible wavelength, and assume other components don't impose a poorer limit. All right, so focal length is 3 centimeters, diameter is 5 millimeters, and we want to find the smallest thing we can see using 450 nanometers. So focal length is 3 centimeters. The diameter of the lens is 5 millimeters, so half a centimeter, and we're going to use a wavelength of 450 nanometers, right? Okay, so Rayleigh's criterion says that the smallest thing we can resolve has an angular size of 1.22 lambda over d. Now in the lecture I wrote this as sine of theta minimum. All right, now it turns out sine of theta min is a little bit more accurate, but we usually only use this equation when angles are really small. Anyway, we've already made an approximation getting here, so your book and most places usually leave the sine off. The time that the sine can be useful is if you don't remember how to convert between radians and degrees and you want your answer in degrees, right? But this is true only if my angle is in radians, all right? So anyway, that's the angular size of the smallest thing I can resolve, and I'm given lambda and d, so I can calculate that. But I actually want to know the size of something. So here's my lens, and I'm looking at some object right here that has some height h, and I'm going to say I can just barely resolve it. All right? Well, this angle here is going to be that angle right there, right? Because this is the smallest thing I can resolve. How big is it? Well, I can find how big it is if I know how far away it is. But remember, for a microscope, we're going to put our object about 1 focal length away from the lens because we're trying to make a real image far, far away from the lens. All right? So tangent of theta is going to be equal to h over f. All right? But we're going to use the small angle approximation again and say that's about equal to theta. All right? So this is theta min, right? So this is about equal to 1.22 lambda over d. All right, and so that means the smallest thing I can see, h, is just going to be, multiply the f over here, f times 1.22 lambda over d. Right? Now notice, I could have, maybe you thought maybe it makes more sense to do things sort of symmetrically and call this h, and then this angle right here, well, the angle that they give you when you're asking about resolving things is really kind of how far apart two things have to be such that the diffraction peak of one is the minimum of the other, right? So I guess what I'm trying to say is it doesn't really matter. You could have called this the half angle and used h over 2, And then we could have said, oh, tangent of this angle divided by 2 is equal to h over 2 divided by f. But then when you do the small angle approximation, these 2's cancel out and you get the same thing. So it doesn't matter whether you try and think of the object as going up from the center or being symmetric or whatnot. In the small angle approximation, it works out the same. And all we have to do then is just solve what is h. So we plug in our focal length, 3 times 10 to the minus 2 meters, multiplied by 1.22 times 450 times 10 to the minus 9 meters, divided by d, which was 5 times 10 to the minus 3 meters. All right, and so the smallest thing I can resolve then is 3 times 10 to the minus 2 times 1.22 times 450 times 10 to the minus 9 divided by 5 times 10 to the minus 3, and we get 3.29 micrometers. All right, is everyone happy with that? So that's the smallest thing we can resolve with this microscope objective. Now, one thing, I kind of whizzed through this. One thing you should do is you should stop before you do your answer. You should stop at this point and say, do my units work out? Length, length over length. Those lengths cancel out, you're going to get a unit of length. That makes sense, all right? If I change things, if I have a bigger diameter, well, that means I can resolve smaller angles, which means I ought to be able to resolve smaller things. So bigger d, smaller wavelength ought to make this smaller, right? If the focal length is bigger, that means I'm got this resolving angle, but I'm pushing it further away, right? So that means for a given angle, I'm going to see a bigger, I can only see bigger things. So I can check this and make sure that it makes sense before I plug my numbers in. Get in the habit of checking your answers when you work your homework, and definitely do it when you work your exam problems. All right, diffraction from a circular aperture. Light with a wavelength of 650 nanometers comes from a very small point on a red LED. You place a foil gum wrapper with a 0.5 millimeter diameter hole in it, a distance from the LED such that the light from the LED at the wrapper approximates a plane wave. A diffraction pattern from the hole appears on a wall 5 meters from the wrapper. What is the diameter of the central bright fringe? All right, so this is basically what we're doing. We have some light from some source, whatever. We go through our circular aperture, and it's going to make a diffraction pattern over here on the wall, and I want to know how wide this thing is. All right? Well, we haven't done circular diffraction, right? Have we? Well, we sort of have. We said Rayleigh's criterion. Theta min is equal to 1.22 lambda over d. So that was derived from a circular aperture. But that's Rayleigh's criterion. That tells me if I had another source of light coming through this thing at another angle, right, its diffraction pattern, you know, if this angle between here and this peak right here, if that angle is theta min, that means that the first minimum of this one occurs right at the peak of that one. I didn't draw this very well. So if the angle between these two objects that are producing this light going through this aperture, if those two objects are just barely resolvable according to this equation, that means that the peak of this pattern happens right at the first minimum of the other pattern. All right, so that tells me how far away the minimum is. So when I calculate theta min, that's the distance out to the first minimum. So that would be the radius of my blob, right? I'm going out to the first minimum. What I wanted was the diameter, all right? So, in other words, theta min is equal to the tangent of theta min is equal to r divided by this distance L, right? And in the small angle approximation, tangent is the same as that, all right? So r over L is equal to Rayleigh's criterion. But the diameter of my blurb is just 2 times r. So the diameter of my beam on the wall out to the first minimum is just going to be 2 times the radius, but 2 times the radius is just 2 times the distance to the wall times 1.22 lambda over d. All right? So I just plug in those numbers, and we said that L is 5 meters. The gum wrapper has a hole which is 0.5 millimeters, so this is 2 times 5 meters times 1.22, and the wavelength of my light was 650 times 10 to the minus 9 meters, and the diameter of the hole I said was 0.5 millimeter, right? So 0.5 times 10 to the minus 3 meters. The meters cancel out, and my units work out. Does this make sense? The bigger L is, the bigger my diameter of the hole will be. It just keeps spreading more and more. If I start with a bigger, I've used two D's. D hole, or D light, because this is the diameter of the hole. If my hole is smaller, it diffracts more, and I'm going to get a bigger blob of light on my screen. Shorter wavelengths diffract less, I'll get less. A smaller thing on the screen, smaller blob on the screen. So this makes sense, the units work out. All we have to do now is plug it into our calculator. 2 times 5 meters times 1.22 times 650 times 10 to the minus 9 meters divided by 0.5 times 10 to the minus 3 meters. And it looks like my spot on my wall will be 1.59 centimeters. Alright, so I shined light through a tiny hole and it spread out to make a bigger blob on the wall. And I was able to use Rayleigh's criterion to tell me how big that blob should be, because I remember with Rayleigh's criterion, if something is off at an angle, making an image somewhere, making a diffraction pattern at a different angle, if it's just barely resolvable, just right at Rayleigh's criterion, as I go through my circular aperture, right, Rayleigh's criterion tells me at this angle, that's where the peak should be in order to be at the first minimum, right, of my other object. So that angle tells me where the first minimum is. I go to the minimum on either side, and I get this, right? So either side, I did 2 times r, because I'm going from here to the other side. And there's my answer. All right, now you should be equipped to do the homework. Let me know if you need help.